In this video, we're going to start work on Chapter 8, and we are going to be looking at types of numbers. So if we look at the South Carolina State Standards, in K through 5, we have worked with whole numbers, we have worked with fractions, and we have worked with terminating decimals, decimals that come to an end like 3.2 or 5.27, 5 and 27 hundredths. All of those are examples of rational numbers, but here in 6th grade, we're going to extend that to include rational numbers that are repeating decimals. We're also going to include in 6th grade our negative numbers. But the important thing I want you to notice is this word rational that starts coming up in the standards in 6th grade. And over and over and over again, you're going to start seeing this word rational. So in this video, we're going to be talking about what rational numbers are and how to tell them apart from irrational numbers, which are going to start coming up in 8th grade. So this is a very heavy middle level idea, not because in K through 5 we don't do rational numbers, we just simply don't use that word. Okay, so let's go for a little math history. So ancient peoples standing outside, perhaps counting their sheep or counting their rocks, how many pieces of wood they have for their fire. And when they counted, they started 1, 2, 3, 4, 5, whatever words they used, 1, 2, 3, 4, 5. And anytime they did this, we refer to those as the counting numbers or the natural numbers. So the counting numbers are essentially the positive integers. You start at 1 and you move forward forever, 1, 2, 3, 4, 5. And we call these the counting numbers because as you step outside to count something, like when small children are counting something in their hand, they start at 1 and they move forward using only integers. We also call these the natural numbers because they're the numbers that occur naturally in the world around us. If we wanted to count how many trees or how many sheep or how many people, those are naturally occurring things, and we would count them starting at 1 and moving forward. Well, we realized very quickly that that was an insufficient number of numbers. So the Mayans in our part of the world and the Babylonians on the other part of the world, they increased our numbers to include the whole numbers. So you guys remember the way Venn diagrams work? This counting number circle is inside of the whole number circle. That means all of the counting numbers are also whole numbers, but there's a number out here that is a whole number that is not a counting number. And that number is 0. You should put 0 in this part of your diagram. 0 is a whole number, but 0 is not a counting number. When you count things, you start at 1, you don't start at 0. So it's interesting to note that neither the Romans nor the Greeks, despite all of their advances, had a digit to represent 0. The Mayans and the Babylonians are the ones who gave us that digit. So there you can see my 0. 0 is a whole number, but 0 is not a counting number. 1, 2, 3, on and on forever. Remember, that's what my ellipses mean. Those are counting numbers and also whole numbers. But again, we realized that those numbers are not sufficient. Sometimes we have less than nothing. Sometimes we owe someone something. So Brahmagupta, who was a famous Indian mathematician, also the Chinese were able to use both positive and negative integers. So you can see I've got some negatives here. You can't tell in this picture, but Brahmagupta worked with negatives as well. And if I put my counting numbers, my whole numbers, together with the negative integers, what I have is the set of all the integers. So again, remember the way Venn diagrams work. 0 is an integer. The counting numbers are integers, but there are other numbers in this part of the diagram, in this circle, that are integers that are not whole numbers and counting numbers. And those are our negatives. So you can see our negatives here. Notice the ellipses this time is on the left-hand side because negative numbers go on and on forever to the left. Okay, so again, at this point, we have all of the integers. So we have a substantial number of numbers, but we also realize there are numbers in between these numbers, both the negative integers and the positive integers, in between 0 and 1, in between 0 and -1. There are other numbers in there. So both the Egyptians and the Arabs were able to work with fractions very early. The idea of decimals came later. John Napier is the one who is generally credited with the idea of coming up with decimals. So if you take all of our terminating decimals, like 2 and 5/10, or 3 and 2700, 2.5, 3.27, And also include with that our repeating decimals, 3.5 with a bar over it, or 4.27 with a bar, then what we have, that set, is our rational numbers. Notice that the word ratio is inside our word rational. A ratio is two numbers compared by division. So a rational number is a number that can be written as a fraction. So you know all of our integers can be written as fractions. You just put a 1 in the denominator. Fractions, obviously, are written as fractions. And we're going to look at in the next video how to write both terminating and repeating decimals as fractions. So the idea of writing terminating decimals as a fraction is an elementary school idea. The idea of writing a repeating decimal as a fraction is a middle school idea. But just realize that we have four basic types of rational numbers, and any of y'all who teach 6th, 7th, or 8th grade, you're going to start seeing that word rational come up in the standards, and you need to know what it is. So our four types, again, for rational numbers: integers are rational numbers, fractions are rational numbers, and then we have two types of decimals: repeating decimals and terminating decimals, that are both rational. Okay, so you can see I have put a fraction, a terminating decimal, and a repeating decimal. Those are all inside my rational circle, but they are not integers. All of my integers are rational, but every rational number is not an integer because the integer circle is completely contained inside the rational number circle. But as time again moved forward, we realized that there are other numbers in between the rational numbers. There are numbers that we can't plot directly on the number line because they never come to an end. So if we take those numbers that are not rational, and you might remember the opposite of rational is irrational, if we take those numbers that are not rational and put them together with the numbers that are rational, what we have is all the real numbers. So the numbers that would be in this part of the circle would be the irrational numbers, and rational and irrational put together are real. So sometimes I have people misunderstand this to think that the irrational numbers are real. And while the irrational numbers are part of the real numbers, remember real numbers also contain the rational numbers because the rational number circle is inside. So irrationals are in the real circle but outside of the rational circle, but that doesn't stop rational numbers from being real also. Both rational and irrational are real. And we can credit the Greeks with coming up with many of our irrational number ideas, especially as they worked with geometry. Okay, again, time moving forward, we have some Italian mathematicians and interestingly also munitions experts, and they are the ones who are credited with coming up with our imaginary numbers. So I for imaginary, and I by definition is the square root of -1. So if I have the square root of a positive number, I get a positive answer. I get a real answer. If I have the square root of a negative number, I get an imaginary answer. You guys are not responsible for imaginary numbers in middle school. That's more of an 11th or 12th grade idea. But just in case one of your students asks about it, hearing about it from an older sibling or an older cousin perhaps, you'll have the idea that they're out there and you'll know where they came from and what they mean, but you're not going to be working with them necessarily. If you remember from what we looked at in the standards in 8th grade, we are learning about irrational numbers. We are not moving into imaginaries. That's a high school idea. Okay, some characteristics of irrational numbers. First of all, there is an infinite number of non-zero digits to the right of the decimal point. That just means it goes on and on forever. It never ends. And also, there cannot be a repeating block of digits. If there were, it would be a repeating decimal, and repeating decimals are rational. Irrational numbers never end and also never repeat after the decimal. So some properties of real numbers. These properties work for both rational and irrational numbers. We've already looked at most of these properties when we looked at our whole numbers, and then again when we looked at real numbers. When we looked at fractions and decimals earlier. But all we're going to say now is that this is included in the idea of irrational numbers. So we do have the closure property. If I add two real numbers together, I get another number that's real. We have the commutative property. You can change the order, addition and multiplication. We have the associative property. You can change the grouping, again, both for addition and multiplication. And notice for associative property, the order of the numbers does not change. When we did this in the last section, some of y'all tried to do associative and commutative at the same time and call it associative. For strictly associative, the order of the numbers does not change. The only thing that changes is the grouping. And that is true not only for the whole numbers and the integers we did before, but also for real numbers. All right, then we have the identity. Here's the additive identity, which is 0. So if I add 0 to anything, it keeps its identity. Same is true for real numbers. For multiplication, the identity is 1. And if I multiply 1 by anything, it doesn't change its identity. True for real numbers, just like it was for the integers and the whole numbers. The inverse property, that's the opposite. So here's the additive inverse. So if I have even an irrational number, square root of 2 plus negative square root of 2, well, that's going to give me 0, just like 2 plus negative 2 gives me 0. It doesn't matter if my number is rational or irrational, I still have this additive identity. I also have a unique multiplicative inverse for real numbers, and this one we did not talk about. So if you take a number and you take its reciprocal and multiply them together, what you get is the multiplicative identity. So when I add a number and its inverse, I get the additive identity. When I multiply a number and its inverse, I get the multiplicative identity. So the multiplicative inverse is the reciprocal of the number that I had before. And again, it doesn't matter which order it's in because of the commutative property. The opposite and the number, regardless of their order, either add together or multiply together to give you the identity, which you see right there in the middle.